So, hello everyone, welcome to Compute 653. My name is Aaron, and this is Yancey. Today we're going to be talking about a paper called Expressive Power of Transformers with Chain of Thought. And this was a work by Merrill et al. Last year. And just to give a brief roadmap of what we're going to be doing for today's lecture, we're going to give you a motivation of transformers without chain of thought and what can be done with transformers without chain of thought first. We'll talk you through the whole chain of thought paradigm. A lot of this class will be related to complexity classes and computational complexity of the different transformer architectures. And so what we're going to be talking about is Turing machines first as well. Give you an idea of the complexity classes we obtain with the Turing machine definition, and then we'll start talking about the results of the paper, and then we'll go through some of the proofs of the results, some assumptions that they make for the transformer model and everything, and hopefully it's a fun lecture. So as we've already seen in previous classes, the transformer architecture is sort of limited in what it can do. So at least without the chain of thought decoding steps. So what the authors show in their previous work is that the class of solvable problems that can be solved with transformers really lies in this class called TC0. Right? And what TC0 is well, it stands for threshold circuits. And what it is a circuit of Boolean circuit, and constant depth of the circuit, and then polynomial in size. And if you were to think of a transformer with just one forward pass, it's essentially one giant circuit. And yeah, as I said, the class of solvable problems we say is in TC0. And TC0, as a complexity class, one of the important results is that there is some sort of lower bound, or it is sort of contained in the class of problems called log space. This will be important down the line when we're talking about the upper bounds of our result. And so yeah, so that's but in recent work, both theoretical and empirical, we've kind of seen how chain of thought really helps transformers with both their reasoning power and basically increases the class of problems that they can solve. And so what the authors want to do is sort of formalize what the expressive power of these transformers with chain of thought is. Specifically, if we're given some number of intermediate decoding steps, say TFN, what is the class of problems we can solve with those TFN intermediate decoding steps, right? So say we have some transformer F, and it takes in some sort of input, like some strings of length, something, and it gives you one token. So the chain of thought paradigm is like, okay, if I want to do a few steps to k plus 1 for some input x, this would be equal to all the previous decoding steps and all the context generated by those previous decoding steps, and then one more step where we take all that as input, right? And so what we're formalizing is, okay, this new paradigm, how much more expressive does it make the transformer model? And this is not a new problem in the literature.
Wait, isn't that f of k plus 1 at the end supposed to be just f?
Also, because this would be the context is taking everything up till then.
So f of k of x, I think outputs something of length n plus k length. Yeah. And then f of k is recursively defined right now. You know, wait, I'm not sure those are the lengths.
Or n plus or say our x has a length of n tokens.
Yeah, that's good.
K, and then this is going to be one extra token.
Yeah, so that f to the k plus 1 should be f at the end, right?
The middle f.
Oh yeah, sure, sorry. That is correct.
Yeah.
Oh, okay. Yeah, that
Thanks for catching that.
makes more sense.
And then they're concatenated.
Yeah, let's call that concatenation. Abuse the notation a little bit. So,
A little bit hard to see the board
Oh.
from here, but.
okay, sorry, I'll write it a bit bigger.
It's all right.
It's alright? Okay, I'll just erase it for now. It's not important, it's fine. So, it's not a new problem, like figuring out what you can do with chain of thought transformers. Professor Dale's done it in the past, and there's a few others works that this paper cites. So in particular, there's one result from Perez et al. In 2021, I believe. And what they do is that they show that you can simulate Turing machines, but they have some assumptions with the positional embeddings where you are basically able to produce these embeddings, which will help tell you which token is a input symbol, which one is a like transition that's been done. And so that looks like you get I, 1 by I, 1 by I squared. Sort of not very relevant and also not readable, sorry.
Nice.
And then also Dale, to use. I think 2023 and then also his current work in 2025. He's shown that you can simulate Turing machines using transformers, but then his assumptions had a bunch of external memory that was also accessible. And so what this paper seeks to do is formalize the expressive power or the computational complexity that can be achieved using decoder-only transformers. And with this, we'll have a few assumptions down the line, but that's generally the motivation of what we're trying to do. I guess one big question we're trying to ask is, can we simulate Turing machines using decoder-only transformers? And we'll give you a proof of whether that's possible. So I'll get it off the end with you.
So before getting to the decoder-only transformer architecture, we'll first introduce the precision level used in this work, because in practice, we cannot represent real numbers precisely because of limited amount of memory. So here in this work, the precision level that we consider is called the log precision. And what does that mean? It means that suppose we have m coding steps in total. Then for each numerical value in this transformer architecture, it's going to be represented by at most, or there's a constant in front. It's going to be represented using at most c times log n bits. So that's the precision level for this work. And then now we get to the architecture.
Why do they use log precision instead of constant precision?
I
Yeah.
think one reason is that parallel work, it shows that log precision can be represented, can be simulated by the TC0 class. So I think we kind of extended on that.
Wait, what?
And I think like parallel work, it kind of shows that the log precision transformer, it can be simulated in the TC0 class. And then I think they're just
The other, like,
The other way around.
maybe that's true, but so Vlad is asking the question because one would be worried about that you cannot increase the precision just like that, right? Like you fix a machine, it has a fixed precision. Okay, what is, by the way, M? M is the length of the input, or?
M is the total number of precision steps. We consider the input and the chain of thought. I'll get to this later, very soon.
Yeah. And so, but it somehow scarces the input or something, or like the total computation. It's not the number of layers. We have D layers that's independent.
Mm-hmm.
And then somehow M is going to scale with input or something.
Mm-hmm.
Okay. But the concern is that I would also share is that, well, in practice we have fixed precision machines, no matter what. So it's a little bit imaginary that we can increase the precision just like that. I don't know, do they
I
talk
don't
about
think
what
they
happens
say.
if you fix the precision? Can you add more layers? Like, would that help? Or
I don't
then
think-
you are doomed? Or
I don't think it necessarily scales with the n decoding step. I think it's just like C log n bits where I think the precision is fixed to some logarithmic amount of.
but like that allows that many
Yeah.
bits,
Yeah.
right? And I bet that they're gonna use that many bits.
So I think it's supposed to scale with input size, from what I remember.
It's input
Yeah.
size, I think.
And I'm concerned about that.
Yeah.
But they talk about why they do it. They say because like when you do a softmax, if it is the case that you would want to equally attend to all the tokens, then you would
Right.
need to represent 1/over input length.
Yeah.
And
You can't even represent the uniform distribution
Yeah.
if you don't have this much precision, if the input is of size m or something.
Yeah.
and then they argue you might as well not talk about like softmax or this like average attention business if you don't have this many bits.
Yeah, it kind of, well, falls short as a good explanation for me, but okay, like as a theoretical, sure, let's roll with it. But you guys understand the concept, right? Like it's not, like, okay, so we have these machines and we wish we had more precision, but are we going to have more precision just because we wish to have more precision? Probably not. Anyways, it's okay. Maybe you can view it like that whatever precision you fix, if the input size is not exponentially larger than precision, then everything that you say is correct. Right? Like you reverse it.
Mm-hmm.
Like whatever precision you fix, you're kind of covering inputs up to a certain size. And it's not actually a small size because it can be exponentially larger than the precision that you fix. So if you say that you have b bits, then the input length is exponentially in b that you allow. And that seems, maybe, that sounds better,
Yeah.
I guess. Okay, sorry.
Okay, thank you. And then now we get to the architecture. So for each input token, they go through for each input token, we'll start embedding and then multi-attention, this and that. And then after all this, we're gonna repeat this block for d times. And then we use a classifier to come out with a single output token. And then autoregressively, we're gonna append this back to the input sequence as our next input. And then I'm just gonna introduce a couple more notations. So here's the total number of the decoding steps, and then there are two parts in that. The first part is the input. When you do the ChatGPT, we just type in the input. So the input length is gonna be n. And the chain of thought, which is also called the intermediate decoding steps, is gonna be a function of n, p of n. So basically, if we say we have n decoding steps in total, it actually means that we have n plus t of n decoding steps in total. Okay, so that's the transformer architecture part.
Right.
Okay.
Is it readable?
So since a lot of these proofs are the only proof we're talking about is going to cover Turing machines quite a bit, I think it's a good idea to just have a brief refresher on what Turing machines are. And I'll do that using a small little figure. Turing machines. So with Turing machines, you have some sort of tape, right? You have a tape head connected to a finite state controller. And in this tape you have a bunch of symbols, say 2, 3, 4, 5, 6. So in each step of the Turing machine, you're going to read your input symbol. You'll make a transition in your finite state controller. you'll write a symbol back, and then you'll either move left or right. -1, and then this +1. And this is a very strong model of computation, right? Formally, you define it using a tuple of some number of steps. So you have an input vocabulary sigma. You have a cape vocabulary, which is just it's your input vocabulary with some number of additional symbols, which are just helpful for computations. You have a set of states Q for your finite state controller. You have a starting state. You have also, I guess, 2 states, accept and then reject for halting. And then you have a transition function delta. And so in each stage or in each step of the Turing machine, you're basically computing this transition function based on a few inputs, right? Or it's better. So we take in our set of states Q, except these two. And then for this case, we only have one input tape, and then we're reading a symbol from it. And what this gives us is a new state. It also gives us a symbol to write. And then it gives us a transition, a tape movement direction, which is either plus or -1, so this one being left and that being right. And so this is a very standard definition of a Turing machine, and it's very simple, right? But in the paper, we use a slightly more complicated version of a Turing machine, given or defined by Hopcroft all in 1977 or something like that. And so in this state, or in this definition, sorry, you have a Turing machine defined by, again, your input vocabulary, your tape vocabulary, a bunch of states in Q. You have a number of final states. You have a blank symbol, which is also part of this. And then you have the number of working tapes. And you have, again, you have a start state, and then you have a transition function. And so in this definition of a Turing machine, you'll have multiple work tapes in addition to your input tapes. So I guess a nice little diagram would be, I have my finite state controller, and I have my input head, or input tape with the input head. But then I also have a number of working tapes with their own heads, right? And I have K of these. And in addition to that, since we're not only talking about like decidability of different problems, we're talking about problems that have some sort of output or multiple symbol length output. We also have an output tape, right? So in this case, our transition function, it takes in the input state Q, except F. It takes in K plus 2 input signals, so K from the work tapes and then input and output symbol as well. And what it gives us is, it gives us a new state. It gives us K plus 1 outputs, or K work tape symbols, and then the 1 output symbol. And then it also gives us a number of directions to which we move the tape head, and it gives us K plus 2 of that. Yep.
Can you remind me what capital F and little b is?
Capital F and little, sorry?
Little b.
Little b. Okay, so Capital F is basically the accept and reject states over here, except we can have multiple of those. So these are all our halting states, right?
Uh-huh.
Or we find out that we're in F and then we can just stop our
Mhm.
transition. And little b is actually in the, well, I guess it's not in the work tape. But what it essentially is just writing a blank symbol or not even writing anything. So just leaving it as that symbol.
Yeah.
Okay?
Okay.
Does that make sense?
And then I guess in the previous transition function, the Q minus was supposed to be set subtract.
Yes. So we have a set of states, and then if we already found out that we are in a
Yeah.
halting state, we don't keep the kind of thing with that.
So basically, the only difference is you have a multi-tape
Tape.
Turing machine.
Yes. And
Well, blank business.
sorry.
Huh?
Sorry, Papa?
The business is a blank character, which is a special character.
Yeah.
But if you write, then nothing happens.
Yes. And the reason why we use this alternate definition of a Turing machine is because it makes our bounds much more legible, I guess. And there is actually a theorem stating that every single tape Turing machine, okay, I'll start with the multi-tape. Every multi-tape Turing machine that runs for TFN steps can be simulated by a single tape Turing machine, but in the quadratic number of steps. So if we have for a multi-tape TN, if we have TFN steps, for the single tape TN, it would be in the quadratic for that given. And this will help us just set a nice bound for our main results later on. Right?
It's interesting that it doesn't scale with k at all.
Yeah. I guess the idea for that is that you have your single tape, and then you'd have these new sort of symbols that tell you the bounds of the tape.
Oh, maybe it multiplies if a big O hides the k, no?
Yeah. Yeah, it does.
It's like k times t squared and
Yes.
something like that.
Yeah. Because with each insert over here, you'd have to do a number of shifts, and I think those shifts are sort of covered by k, but then it's more just how many steps you're doing, which dominates in the end.
Yeah.
Mhm. Right. Do we have any?
In the input size, or the number of tapes.
Sorry?
And what is the meaning of n?
Little n. Little n over here, that would be the number of, little n would be the length of the input tape, or how many
Okay.
characters you have on the input tape already. Yeah. And TFN just means how many steps you've done with the Turing machine.
I didn't really understand this simulation of the single tape machine. What was that drawing that you drew over there?
Oh yeah, so you essentially have like a boundary for each of your K tapes. And so with each transition, or with each insert, you'd have to do a number of shifts for that boundary. And so that would be, sorry, I don't have the theorem or the proof right off the top of my
Yeah,
head.
but like it's basically, well, fine. I just wanted to know what the construct, and then we can think about how that works. So every tape is going to be a contiguous entity
Yeah.
that you're using, and you have k of them, like there is some separation between them.
Yes.
And then if you need more space, then you kind of just like have to move everything.
Yeah.
And I was thinking that, interesting. Somehow, I guess it's like if the Turing machine, the multi-tape makes Tn steps, then in the worst case it can move T spaces apart, and that's it. Like that is, and then like to do all the insertions as much possible, I guess. Yeah. Like I was worried about like that some of like they move really fast, some of the heads and some of the tapes, but like
Yeah.
it just cannot happen
Yeah,
because
I
you
guess
only have
each tape would be of length at most like TFN to start with.
That's right.
And then you have
Yeah,
two,
yeah.
so you have
Exactly.
k times t of n of those. And then some other like,
Right.
bounds.
And that is overhead by.
Yeah, there's overhead, and then at worst you're doing an insertion in each of these tapes, which requires doing that many shifts, and you're doing t of n of those shifts. So then you get a k and then t of n squared term here, and that's how it dominates. Does that make sense?
Yeah, okay.
Right, cool.
Absolutely. Yeah.
Okay. Are there any other questions pertaining to Turing machines right now? If not, I can start with the complexity classes we get from these.
Mhm.
So, do you wanna erase this? I'll erase it, it's fine. Okay, so, with this Turing machine notation, we get a few complexity classes, which are important for our proofs. The first of them is time t of n, right? So time t of n is basically the class of all languages. So that we have a Turing machine which runs in at most t of n steps and then recognizes that language L. So I don't think I need to write that down. That's one of the complexity classes. We have space S of n. So space S of n means that we again have a class of languages L, for which we have a Turing machine that recognizes that language using a tape size of at most S of n. Right? And then we have another definition, time tilde of t of n. And time tilde of t of n is trying to basically capture this like polylogarithmic class in which we have, again, t of n steps, but we have some like additional logarithmic overhead for that. Does that make sense?
Mm-hmm.
And the final one we have, which is needed for our bounds, is chain of thought t of n, which means the class of languages L that we recognize with a chain of thought decoherently transformer in t of n intermediate steps, right? So, I guess I'm erasing all of this for you to write down. Should I write that in this? Okay.
Okay. So now we get to the main result part. So in this statement, there are in total 3 bounds, 1 lower bound and 2 upper bound. And this lower bound indicates that for decoder only transformer with t of n number of intermediate steps, they can actually simulate the Turing machine with t of n steps. So that's the lower bound. And for the upper bound, it means that for Turing machine with either space, this much of space constraint, or this much of time constraint, they can simulate the transformer with t of n intermediate steps. So that's what this theorem says. So essentially, we bound upper bound and lower bound the expressive power of this decoder-only transformer with T of n intermediate steps. And then now, I'm gonna give you some instances of T of n to intuitively show you that, oh, the expressive power of this transformer actually increases as T of n increases. And note that I'm not gonna, for each instance of T of n, I'm not gonna use all three bounds. I'm only gonna talk about the bounds that lead to some meaningful result. Okay, so for the first one, so let's say this T of n is logarithmic with respect to n. We can say the big figure, but just to simplify it.
Oh, by the way, so for the transformer to accept an input, the definition is that like after so much computation it outputs a special symbol or what?
Not a special symbol, it's
What?
whatever output the Turing machine would be outputting as well. Whatever output of the Turing machine is, our transformer can also simulate the Turing machine and then give the same output.
Oh, it's not a recognition result?
No, it's not a recognition.
Usually, like,
But time is
these are
defined for
languages,
decision
right?
problems.
Like the
Yeah.
strings accepted by the Turing
Yeah.
machine with that much compute time and so on and so forth. So I said that for the chain of thought it's the same.
Yeah, that is a good observation.
I think in the paper they said that it outputs the special character number 1 for accept.
Yeah. They say that, but then in their proof for the lower bound, they specifically mention how we're having some, say, m of x length output from the Turing machine. Our transformer can also output that same m of x.
I mean, like that's part of the proof, right? Like
Yes.
how you're using the chain of thought, like extra characters, like essentially
But yeah,
reproducing what the Turing machine would do. But I was just wondering what the definition of what is this chain of thought TN. You said it in words.
yeah.
That is a set of languages such that this chain of thought computation in TN steps does the acceptance, but like, what does that mean?
Mhm.
So I would just,
Yeah.
I imagine it means that it outputs a special character like 1, but I just wanted to make sure.
Yeah. Yeah, that is the case that their definition
And it
is
seems like-
slightly different.
Yeah, it must be that.
Yeah,
Mm.
it is. Their proof will work for the same case where you're just doing the one output symbol as well, like if we were talking about that.
For sure. I mean, like an extra output, like if you simulated every step of the Turing machine and then you're like the Turing, like you simulated it stop, then like you need to append one special character.
Yeah.
You can probably do it.
Yeah, it can be. Right.
Okay.
Okay, so let's continue. So for the T of n equals to log of n, we are going to use this upper bound. So this means that the languages that chain of thought can recognize is going to be a subset of this set of languages. And by definition, this is defined as the complexity class of L. So what it means that previously when there's 0 intermediate steps, like our chain of thought of 0 is going to be upper and lower bounded by TC0. And now, what this indicates is like the upper bound, it expands slightly from TC0 to this L. Okay, so that's the log part. And another instance is, what if this is linear?
So is this a good or bad thing? Like what if
They talk about how.
What if space is? What if this is just like a weak upper bound?
I mean, like, yeah, like it's going, the inclusion goes the wrong way. Like, if you want to argue that this is big, like it's in a big set, but like, is that set also big, or it's a small subset of the big set?
Maybe more potential.
I guess the reason I asked is there's a paper that came out like a few months after this one that showed that it's actually a subset of TC0, so this was loose.
Okay. Yeah, I think this paper also mentions how
Because
they're not really sure. Given
The log n square doesn't give the transformers power? Is
No.
that what you said?
Chain of thought log
Yeah.
n is exactly the same as chain of thought constant.
Yeah.
Yeah, okay.
Mm-hmm.
Okay, so for the linear part, we're gonna use this bound and also this space bound. Okay, so what does this bound tell us? It tells us that because the simulate thing, the finite state automaton actually belongs to the set, which means that the chain of thought of linear steps, it can actually simulate the finite state automaton.
So that's regular languages.
Yeah. So basically, we're saying can recognize regular languages. Okay, and then we're gonna see the upper bound, the space of n, and it's known that this is gonna be a subset of the context sensitive languages. So what this means is that the chain of thought with linear steps, it can recognize languages somewhere between regular languages and context sensitive languages.
By the way, space for any poly Tn is a subset of context sensitive languages. Is that also true? Or only for n? I would think that the context sensitive language is a big class, and or any you would write any, I don't know, polynomial there, still be true?
Yeah.
I don't know because P space is bigger than NP. But I don't remember how NP relates to context sensitive.
Okay.
Yeah.
Yeah, maybe the space business is weird. Okay. Yeah, this is beyond me.
I have a question though, is recognizing regular languages like a hard task? Like what I mean is you now added linear steps to chain of thought. Did we get something that we weren't able to do without the linear steps?
Like if space log n is smaller than time n.
So the question is whether TC0 can also do it.
Yes.
No. I think from their proof they say that it can't. No real concrete proof for now that it can't. I have to say it's in this other complexity class called NC1, which you have logarithmic depth of your circuit, and it's capable, or that class is capable of simulating the finite state automaton, but not GC0 with the constant depth. But again, that's another thing we're not sure about.
What's CSL? Is that just like a bigger class?
We're just calling context-sensitive languages, yeah, a bigger class than spaces then. But we're not
It's
too
the
sure
set
about
of
that.
all languages that a Turing machine with a linear amount of space can solve. Well, I guess that's exactly what that is.
What was the definition?
It was what Bale was talking about, the linear bounded output,
Yeah.
right?
Yeah.
Maybe I just throw a question mark over here.
No, but like in automata theory, like just for like there's people like study finite state machines, and then they study state machines that are called push down automata or something that have stacks,
Yeah.
and those are the context. And then they study the ones that have linear space, and then they study full Turing machines,
Yeah.
and each of them have like discrete jumps in capability.
Yeah.
And the languages they recognize are
Mhm.
there's a relationship.
Mhm. Yeah.
So what do you mean by recognizable language and that squiggly line CSL?
Squiggly line kind of does not make sense. It's just trying to show that with the linear steps, we're somewhere in the bounds of being able to recognize regular languages but not context-sensitive languages.
And the goal is to recognize context-sensitive languages?
There's no real goal, it's just like showing you where the bounds are at, and it's sort of undefined in this case, because we don't know specifically where CSL is compared to.
Okay, so if you could recognize CSL, would that be better though?
Yeah, I mean, it would mean that our expressive power is
Yeah.
a bit better than just recognizing regular languages. So I guess the next point is going to show that we can do better than this.
Okay. The next one is, what if delta n is polynomial of n to the power of c for some c? Then we're gonna focus on this lower bound. So this is a lower bound, and what does it tell us? It tells us, so basically by definition, I think that's the definition. If you take the union of all this over C, that is how P, the class P is defined. It means that chain of thought of n to the power of polynomial steps, they can solve P.
Mm-hmm.
Okay, so is there any discussion around the main result?
The upper bounds of the main result.
Okay.
Sorry, for the upper bound, I think, do we know any relationship between a space and time tilde? They are not,
No.
What do you mean?
I mean, probably they are not subset of each other because they would say the lower one, I guess. But,
Well,
I mean,
we know now. Well, we know that like you can simulate time t with square root space
Uh-huh.
for anything. So like if you have something that runs in n squared time, you can simulate it in square root of n squared space.
which is,
Which was a
that's
result
why we
from-
have Tn squared and Tn in the space.
I mean that I don't know. I mean that well, that's just part of the proof.
Mhm.
But I guess that's their. Oh, I guess you're asking whether time is bigger than space or space is bigger than time.
Yeah.
One is bigger than the other.
Yeah.
If you're using n time, then you can't use more than n space.
Yeah.
Yeah.
But if you're using
Huh.
t of n squared time,
Then you can still do it in t of n space.
Yeah.
But then the time may be much bigger for that simulation.
yeah.
Mhm.
Also, maybe from here, the way you presented it, it seems like there's lots and lots of relations. But I guess there's like one key idea for upper bound, which is that you can simulate a chain of thought neural network with a Turing
Turing
machine.
machine. Yeah, and that's what we're.
Yeah, but that's kind of like, I mean, we do that all the time, right? I have a Turing machine in the computer, which simulates a chain of thought. So of
Yes.
course you can do that, right?
Yeah.
And then the other way it's saying that you can simulate a Turing machine using chain of thought.
Yes.
But the important idea there is that you're going to output one symbol in your chain of thought for every step the Turing machine takes.
Yes.
Which is why the time turns into
Yes.
that more space.
Yes.
And everything else is follows from that.
Right.
Okay, so now we're gonna prove the upper bound first,
Mhm.
specifically this one. So the whole proof idea is to use a Turing machine to to simulate array operations in this decoding only transformer. And
Oh, sorry.
okay, so among all these operations, this multi-head attention, the self-attention part, it dominates. Because basically, suppose this is our input. It has to send a query and then it has to go through each of the previous tokens. So basically, that's gonna be linear on the left. And for any others, that's gonna be like the constants on it with respect to the input. Because we're just focusing on this current token.
Sorry, I didn't get what we are doing.
So basically, I'm trying to see which operation is the most expensive in this transformer architecture.
In terms of what, time or space?
The input left, like the time.
Mhm.
Okay. So basically, I'm just trying to simplify the curve. Is that it's sufficient to only consider the self-attention operations. So basically, here's the algorithm. For each forward pass I, and because the whole input, it can be at most n plus t of n, right? So at most, they're gonna be this number of forward passes. Because we're gonna do this again, again, and again. And then for each one, we append key I onto a word tape. And then we append the value I onto another word tape. And then we compute the query I. Right? And then we're gonna append to all the tokens before that. So key J, mother J. And this, again, at most, it's gonna be m plus t of n steps in total. And then for each pair, we're gonna use add and multiply to compute the attention output. So that's the attention formula. And then we're just gonna add this to some tape that contains this sum. Sorry. And then after you attend to all the previous tokens, the final sum is the desired output. Okay, and basically for this for loop, we're gonna loop for at most n plus t of n squared. Right? And then for each multiplication and addition, because we're using the log n bits, we're using the log precision transformer. And there's a thing, it's called the p bit
Mhm.
for all the p bit numbers, they can be added in equal p time and multiplied in p log p time. And this one is smaller or equal to p squared or subset. And then that happens inside of this inner for loop. So basically, the whole time complexity of this computation is going to be n plus t of n squared, which is the number of this inner loop, times the cost of this one, which is going to be p squared, right? Let's just say p squared. And for this p squared, for this p, because we are using the log precision transformer, so in total there are n plus t of n steps. So basically, p equals to log n plus t of n.
Mhm.
Yeah, and then if you plug this in, this is where this tilde thing come from.
But this is multiple Turing machine, right? Like multiple tape Turing machine.
Yeah.
So aren't you gonna square it with if you want to use a single Turing machine with a single tape? Like did I lose some, like did it miss something? Like
Their upper bounds use multi-tip Turing machines.
okay, I see.
Yeah, if I recall, I think the time classes usually use that
Yeah, single Turing machine.
multi-tape or one tape.
One tape, single Turing machine.
Yeah, like a or a multi-tape one. I don't remember.
So in their definition, it's multiple tape.
Yeah.
So
Yeah, because like the simulation result was taking the quadratic time of the single tape machine, right?
Yeah.
So it's like these bounds are then, oh, okay, how to understand it?
Well, the question is, what is
Like
the
you have to square it. Like if this is already squared, then you still have to square it if you want to convert it to single tape.
yeah.
Then it would be
Yeah,
to the
for-
power of 4,
Yes.
not the second.
Yeah.
See?
But it just matters what Turing machines you consider. I can't remember what is the classic one that is considered for most complexity theory
It's
stuff.
definitely single tape.
I'm actually not sure. But maybe you're right.
No. Definitely single tape. I would be
We
very.
were talking about Turing machines way before 1979. When
Yeah.
this machine was introduced.
But
That's
this
true.
looks like super vanilla. Like, do you not like have some tricks that you can speed it up? Like, this looks super vanilla.
it is super.
Like the bounce sounds like loose. I don't know.
Wait a bit. No, I was thinking about like if you just count how many operations these machines are doing, they are doing a lot of operations. So if you actually need to simulate the details of it, this is how much compute you are gonna do, right? Because in this attention, like you don't have to look back, you have to do all these calculations. It's gonna be quadratic. So it just says that like if you write this program, this is the amount of compute you're gonna do, and then we told the story with Turing machines as well, right?
But it should not be necessary to use a multi-tape Turing machine. Like, I'm pretty sure you can do quadratic compute with a single tape Turing machine.
I would think so too.
But in
I
this
think
case, they
it's,
happen to use multi-tape because it makes their life easier. But yeah, You don't need to
Yeah.
further throw in the further quadratic penalty for simulating this on a single tape Turing machine, because I'm pretty sure you could have done
Right.
it on a single tape Turing machine.
This is just a loose proof.
Yeah.
Yeah.
New project.
It doesn't seem real that, yeah. Mm-hmm. Well, okay, it's a boring project, don't get too excited.
Okay, so we proved this upper bound, and now we have two options. Because it's already 4:30, and then I was wondering, should we jump to the?
I guess I'll give us a very brief explanation of why the space one holds.
Mhm.
So the space one, essentially they're doing no caching, so they have this amount of space for the number of intermediate decoding steps they're doing. And then, as we saw before with the result from the TC0 thing where the transformer can be represented or in log space, we have the log n part there. So that's a very hand-wavy explanation, and we're not gonna cover all the nuances of that.
Uh-huh.
I think it's better to just skip to the lower bound proof for now.
Mhm.
And I'll need all the space for it.
Yeah, I don't know. Looking things up while we're talking is apparently for time. People usually consider multi-tape stuff, but for space they consider single tape. I don't know.
Alright, so before we get into the actual lower bound, we need to make a few assumptions of our transformer, which will help us to actually retrieve what tokens we want when computing the attention score to like figure out our transitions. So the first one we're gonna do is saturated attention or averaging hard attention. Basically means that for our similarity scores, we're not gonna be using a softmax to get a nice distribution. We just want some maxes, right? And so each query key score with the similarity is gonna be either a 0 or it's gonna be like 1 by V for how many V tokens are max. I think that's the definition for what V is. And that's saturated attention. We don't want a nice smooth distribution, we're just looking at maxes so that we can attend to those. The next one we're gonna do is strict causal masking. And causal masking means you're not attending to future tokens. In the strict causal masking case, you're not attending to yourself either. So you're only attending to prior context without attending to yourself. And once I get to the proof, it's gonna be much nicer to see why. Projected prenorm is another assumption that we're gonna make where you're basically able to construct some sort of feature extraction from your input signal. So you're gonna do a linear layer before you actually go to the norm layer. And what this allows us is to have an even more like relaxed definition where we're using multi-prenorm, so you have multiple projections from your input signal before going into a layer norm, so you can get multiple outputs. And that's, those are basically the assumptions. I'm kind of skipping through this quite a bit. And they make another modification for using layer norm hash. So the traditional layer norm, what it looks like is, so say we have layer norm x, where x is some vector. This is just equal to x prime by the norm of x prime, where x prime is given by x minus mean. And we're going to use an alternate definition for the case that we're using saturated attention. So with saturated attention, you get the nice ones for wherever you want to attend, but you also get this denominator, which makes it so that you can't get an exact similarity check between the two, or an exact equality checker between two different tokens. So what they use is this layer norm hash thing. It's defined as this. So for two scalars, x, y, we have layer norm x, y, negative x, negative y. And so what that gives us is like this nice, well, it's zero mean because we're doing minus and minus. So you get our negative x, negative y. And then we'll also get like a square root of 2x squared plus y squared. And so what this nice little layer norm hash allows us to do is do a scale invariant computation. So if we have some phi x by I, 1 by I, that's just equal to phi x1, because over here you get like a by I squared, take it out, and then you have the I denominator over here as well.
It doesn't have to be 1, it's just arbitrary y, right?
Yeah, that's an arbitrary y. They can both be like, I use one for convenience because that's another definition, so I'll get to that right now. So phi of x we define as x1. And that's something I'll come back to for the equality check. So basically we have our I from the denominator canceling this out, right?
Mhm.
So it's a nice scale invariant computation. The next thing it allows us to do is an equality check. So if we have phi q and then phi k, we get 1 only, I guess if and only if. So that's if q equals k. I'm not gonna expand the whole computation, but that's basically what it allows us to get. And so now I think we can proceed with the theorem. It's a mouthful, so I'm just gonna read it off. So it says, let M be some Turing machine that on input length n plus 1, it runs for at most t of n steps, and this t of n is at most polynomial. There exists a decoder-only transformer which has saturated attention, strict causal masking, and projected prenorm that runs for that on the same input $x. It takes t of n decoding steps, and then it will produce m of x. So write that down a little bit nicer over here. We have a Turing machine m, and we have some input x. We get m of x for the Turing machine with our chain of thought transformer with all these assumptions. We're going to run for t of n decoding steps on input $x, and then we're going to output m of x as well. And so this $x thing is mainly just used for being able to use zero indexing, and it helps with some of the indexing problems we'll look at when we're trying to find our keys, queries, and whatnot. Any questions about the assumptions made and like the layer norm hash part?
Well, what is D? Like,
I don't understand, where is this Leonor hash going to be used?
It's going to be used before our query, or before our attention.
It's in the diagram.
Oh yeah, is it?
Isn't it the linear thing? I
Oh,
was looking
the-
at that
oh,
for a
yeah,
while.
yeah,
In there?
I guess in this
After a
case-
layer norm, before MHA.
Yeah.
Okay.
what is D? Like, I don't know what layer norm is. Like, is it like the input dimension? Like, what is the like, or the number of neurons? Like, whatever.
D in this case is just some working dimension. It really doesn't matter for the.
Oh, so the working dimension is not like the input dimension.
No. For their thing, they're only going to consider scalars anyway, so this is just a definition for having some vector x.
Well, my question probably is like, is D larger or smaller than n? Like, what's the relationship between D and n?
It's probably smaller than n. We have our.
It's fixed.
It's
It's a constant. It doesn't
Yeah.
grow.
Yeah.
It doesn't
Okay,
grow.
cool.
Sorry, that's a confusing notation. I'll probably just erase it. X is a vector, right?
No, my question is like, basically, I don't know what layer norm is. So.
Layer norm is like.
It's defined over there. It's on the board.
Yeah. It basically normalizes
That-
per channel
the-
signal, right?
Come on, you
X
look on
bar,
LLMs.
you should define what the X bar was. It's a vector, right?
Yeah, x bar would be the mean of x.
I'm really sorry to regret that. ask.
That's just a single number.
Yeah, it's a single value. So we're subtracting
How-
the mean.
We're subtracting a single value from vector.
Yeah. Like
Isn't it
it's
the-
element wise.
Isn't it the mean x at that layer? Over all the tokens or something? And then you
That's what I
normalize.
mean,
over each
but
channel.
there's a dimension problem.
Yeah.
Is there?
I mean, if X is a vector, like mathematically you cannot write that you're subtracting a
How? Let's just use some.
single number from a vector. Yeah, you can, each component is X bar. Yeah.
And that's the same dimension as x in this case.
Yeah. Yeah.
So That's element-wise subtraction, where you're, from each element you're subtracting XY. Cool, 7 minutes. Is that fine?
And what was the, my internet broke. What was the equality check?
Oh, equality check. Basically, if we have, we're gonna use this like sort of identity layer norm hash where we're just using 1 with the x. And in this case, sorry, x is a scalar. It basically gives us like some, if we have the product of 2 of these hashes, they're only equal to 1 if we have q and k being the same value. I could verify this, but it's slightly, we're running out of time.
Okay, fine.
Or maybe I'll come back to it later if we have time.
When is it gonna be used? It's like a lookup, your Q matches your K.
It's going to be used in our attention heads, making sure our query matches some of the keys so that we can get a 1 where they're equal, right? So basically, if we have some, so okay, I'll start over with the lower bound now. So in our theorem, what we're going to do is try to simulate the Turing machine with our chain of thought transformer. And the way we do this is we have some input called $x. And this is going to be $, and then our input tape, whatever's on there. So let's say symbol 1, sigma 2, 3, all the way till some sigma n. And then after we churn through our input tape, we're going to start writing some diffs over here. So diff 1, diff 2, and these are just going to be the transition outputs, right? So the vocabulary for this diff is defined as that, which is q x k plus 2, or it's k plus 1. It's k plus 1, I think. K plus 1, tape symbols outputted, and then 0 or then plus minus 1. Tape position, or tape head moves 0 or plus minus 1, right? So that's the diffs. It's basically the output of our transition function, right? And we'll be writing a few of those. Ignore this indexing because it makes no sense for right now. So in the inductive, we're going to use an inductive proof for this. And our first case, which is the base case, is that we have our I step is before the intermediate decoding step, so I is less than or equal to n. And in this case, we're just going to parse through our input tape and have this diff del 0, which is q0. We're writing nothing, so it's that blank symbol. We're writing k plus 1 of those for each of those tapes. And then we have no tape input. So it's sort of like just getting our input out of the way for our next step. In the inductive case,
Where is delta 0 output?
The first step is that you took the Turing machine and you changed the Turing machine so that it's kind of normalized in some way, so that it will be easier to deal with.
It's sort of like computing n forward passes with just limited context, but I sort of really don't understand what they say for the base case. It's just more that you're not really outputting anything looking at just this. It's sort of like, I guess, the teacher forcing thing where you write a symbol del 0, but then it's not really realized in the input context again, right? You sort of just give it del, sigma 2 again. At least that's how I understood it. So we don't actually write anything to our output yet, or to our context yet. The first time we do that would be with this diff del 1.
I'm really confused. I said that we take a Turing machine, and the Turing machine is going to do, I don't know, whatever it wants to do, right? Like it reads, writes, moves, doing its thing, changes the state. And then we somehow want to emulate it with our transformer, with this chain of thought business. You know, of course, there is a problem that, well, I guess like the transformer sees all the inputs right away.
Yes.
But now it needs to kind of like the Turing machine is like, don't know, it reads the beginning of the input and like, okay, it needs to catch up, whatnot. But like, I would have imagined that like we want to very closely somehow emulate what the Turing machine is doing, maybe write in the output of what the Turing machine would be doing, and then everything else that we need to keep track of what else needs to be done.
Well, that's what all these deltas are, right? It's exactly the behavior of the Turing machine at each step.
Yes.
Okay. But like, how can I assume that the Turing machine is outputting blank and stuff like that?
Well-
First 10 steps, it's not, right? How do I know that?
I'll leave this one.
It's doing its thing.
Mhm.
Also, it's a K-tape Turing machine, or?
Yeah, it's a K-tape Turing machine.
Okay.
But
Okay.
I guess the first two parts of the proof can just apply to single tape Turing machines. But
I thought the base case here was basically, because for your chain of thought, the input is there as a prompt, and
yeah,
it's already there.
yeah,
But you need to transform basically the same input into a different representation.
yes,
So that you can start treating it as if it's all on your tape.
yes,
Right?
yes,
Because so you need to annotate all of the symbols in your input with like memory locations and things like that, right?
yes.
So it's just transforming the input from chain of thought tokens into Turing machine tape tokens.
Yes.
I suspect.
That's sort of the.
Can you repeat that? Because I couldn't hear.
Repeat it.
It's basically taking our input space, which is
Yeah.
in like this chain of thought step where you have all this context already, and sort of converting it into a Turing machine tape where you sort of have it on your input tape already. The base case.
Kind of working the other way around.
So Shaba, so the way I thought about it is that, so when the chain of thought starts, you already got the input as a prompt. But when the Turing machine starts, the input is there on the tape.
Yeah.
And the mapping between how things are represented on the tape versus how they're represented in the prompt is not like one-to-one. So you need to annotate the symbols with things like memory locations and stuff like that. So this initial phase is just taking the prompt and turning it into a bunch of symbols that stand for the same prompt but now stored on the Turing machine tape.
Okay.
So it adds in like memory locations, it adds in head locations, it does all sorts of things.
Yes.
I mean, like we would need to annotate the head positions and whatnot. I don't know how, but yeah.
Yeah, so the first
Right.
n symbols of the prompt will turn into something like n symbols, but they are just like richer symbols that have more information associated.
Yeah.
Okay.
This construction where we're doing like a dollar and the symbols, this is not exactly from the paper, this is just to help with our intuition of how we indexed using I. So that first thing, the base case is assuming that we did convert our prompt into some sort of input tape in the Turing machine, right? Because for the transformer, you already have this as a prompt, and then you start doing your intermediate steps. For a Turing machine, you just have to iterate through all of those. So it's slightly different for this case. But I guess I'll just skip to the inductive case, even though it hasn't been clarified too well yet. So in our inductive case, we have I greater than n, so we've started doing our intermediate decoding steps. And so what we want to do in our intermediate decoding step is first we need to retrieve our tape head position. And that we will call hi of tau, where tau is basically the number of tapes we have. And for the input tape, that would be hi of 0. Then we need to retrieve the symbol at hi of 0 so that we can compute the transition, right? And then these two are basically for input tape. And then the third one, what we need to do is do the same for word tapes, right? So let's see how we retrieve the tape head position first. So say we're in step I. Our query for this would be, so in our attention head, we would be querying uniformly over all the prior tokens, right? We would want to only consider tokens in which a transition, a direction was encoded for the movement of the tape head, and that's only given by these tokens, so we only care about whether they're a diff token or not. And so for our key, we're going to have the indicator function that xj does not belong to our input vocabulary, and the value we will give is just plus or minus 1. So this will build a little intuition of what this is. Say we have our head output. We have a value, and then we have our token. So say our token says state Q1 and then move right. The next one says state Q2 move right. I'm just gonna say Q5 move left. Q7 or something move right. The values for these would be +1 since we're moving to the right, +1 since we're moving to the right again, -1, and then +1. And so what we want from our output head is basically the position that we were in at the start. And so what that would be is say 0 over here, 1 over here, 2 over here, and then 1 again over here. But since we're using our averaging hard attention, we'll get denominators over here for the number of tokens we've attended to previously to get this number. And that would be over here 0. It would be 1 token attended to over here. This would be 2 tokens, and then this would be 3 tokens, right? So what we want to do is just look at our current input, and based on the calculations of which direction they've moved in, we try to assemble hi of 0, right? So in our query, we would have, say, +1, -1, +1, etc. We are attending uniformly across all of these, but then only these ones will give you some value, only these ones have a key that's not 0. So our QK will only consider these. And what our values give us is the final position of the the final tape head position. But since we're doing strict causal attention, it only gives us the position up to the last state. So that would give us actually hi minus 1 of 0. And then you'd have the denominator of I, since you've attended to I tokens. With the 0 indexing, it becomes I. And so with our feed-forward network, given our current input, we will write to a residual stream hi minus 1, 0 by I, plus 1, and then we'll also write hi minus 1 by I, minus 1. And they say that the linear layer using the current diff token will tell us which one it is, whether it's this one or not that one, right? So effectively we construct at the end hi of 0. So this part is done.
Oh wait, I don't.
Wait, how is the divide by I done?
The divide by I done because we're attending to I tokens at the I step. So we get, with our hard averaging attention, a denominator of I.
Yeah. So, but don't you want to get rid of the denominator?
Yeah.
We will do that when we're retrieving the symbol at h of i's, right?
Oh.
Yeah. So technically in our string we will have this value at the end, but the I is sort of irrelevant in the denominator since our layer norm hash will be able to remove it, right? So the next thing we try to do is retrieve the symbol at that head position. And so for that, I'll just group this as step 1. So for this, we do a query. Or first I should give you the layer norm hash. So what can I erase? I'll just erase this part. So now when we're going to the next multi-head attention layer. We're going to do the layer norm hashing part first, and we'll define our hash in the following way. So say I of 0, we'll define it as phi of hi0 by I, comma 1 by I. I by I, 1 by I, if xi belongs to sigma, right? So what that does is for all our tape symbols will encode their position using the layer norm hash. So this would be 1, 2, 3, etc. And then all of our diff tokens, they will be encoding their tape head position. So this is H1, 0, H2, 0, all the way to HI minus N0. I'll just remove this R. That's a nice N. All right. So what this allows us to do is in our query, we will set the query to just phi I of 0 and then -1. And this is just concatenating our scalar from here with the -1. For our key, we will do phi j0 and then an indicator function saying xj belong to the tape symbols. And then for the value, we'll be doing phi j0 and then sigma j, right? Are we clear for what we're doing up till now?
Yeah.
Okay. So what we'll get in our query and key is that we're, with the similarity, is that we're multiplying them together and we get this product. So phi I0 and then phi j0 and then minus indicator of xj belonging to, right? And so what that gives us is if we have a matching head position with whatever other layer norm hash is propagated from these tokens, we will get a 1 over here. But there's a case where you're looking at a diff token and it also has the same tape head position. And that's a case we want to avoid because we want to retrieve the symbol at the end of the day. And so this part is 1. And that gives us a attention score of 0 or similarity score 0. But if it does not belong to, if it does belong to the, okay, that was, okay, that, sorry. So if the token belongs to our diff tokens, we will be subtracting a 1, and if it's not, we will just be subtracting a 0, and that gives us 1 for our tape symbols, right? And so the value propagated by that is also going to give us our tape symbol. So in this way, we've found our tape symbol as well. Cool. And I'll sort of just speak to the third case. So the third case is when we're actually working from the work tapes. And so in our context, our input symbols are pretty much.
Wait, I still have a question about the, what is that phi, that gives you the symbol somehow?
Which one, sorry?
The phi I times phi. So I see in the case where it's on the, one of the diff things, then the I and J are this like H J over J thing or whatever.
Yeah.
And I version, and then the I's don't matter because of the layer norm hash.
Yes.
And so, and those are the positions now, the HIs, so then they finally match. But then you're gonna get a bunch of positions that match, potentially, that like if the position head was there before. And then what does this quantity give you? Like, okay, I understand you get 1 when you match some position from before.
And this quantity gives us 1 if that token that was appended to is a diff token, right? So if
Yeah,
we're
the indicator is 1.
Yeah. The indicator is 1, and then it's 0 if it's not. So if it's a tape symbol, and we only want the tape symbol to be matched because we're trying to retrieve the tape symbol, right?
Oh, right.
So this gives us a 0 in the case where we had, say, hi of 0 equals hj of 0. So we don't want this case. We want-
Right, I understand.
And this gives us 0, but if hi of 0 equals the token position, then that gives us a 1. And that's what we want.
Yeah.
Right? Sorry, I erased it. Okay. Running out of time, so I will just erase. I'll erase this part. And for the work tapes, this is sort of something we're just going to glance over. We have our layer norm hash defined as the same case if we have this, so how I 1 by I if we are actually no, it always does this. And then it also gives us this other one, which is phi. This is not right. They're not right. This is that. And then we also have another hash, which is given by psi. So psi I of tau is equal to phi f of I, and then 1. And we're not going to go into detail about what this f of I is, but the main intuition is that since we're only considering the diff tokens here for our work tapes, we want to find the last times we were at the same tape positions, right? And so this f of I is basically a tiebreaker function, which will give us the rightmost diff token, which encodes the same tape position.
Mm-hmm.
And so with that, we can start finding the last diff token with the same head position. And since we're using strict causal attention or strict causal masking, we're not just seeing our own token and saying, oh yeah, we're in our position, we'll use this one. So say we have another token along the way, which is hi0 as well. We match with that one now, given our tiebreaker function. So that's the gist of their proof for being able to simulate the Turing machine with a chain of thought transformer. And so once we do all these steps, we are given the current state, which is just encoded in the previous symbol, right? We have our input symbol retrieved. So we have we have sigma I. We have all the work tape symbols retrieved. And then we can compute the transition using some pre-core network. Right?
Mm-hmm.
Well, aren't you gonna implement F2 on your Turing machine, or like on your transformer? It sounds like magic. Like you just have a tiebreaker function.
Yeah, it is kind of magic what they do, but their conditions for f of I is that it should be able to, you should be able to compute it with a single transformer layer, so both the attention head and your linear layer. And it also should be monotonically decreasing, so that when you're actually using it to break ties, the last one will have the least value for f of I, so that it breaks the ties easily.
So that's basically done using position encoding, right?
Yes.
So when we were talking about RASP and stuff, we said that we can implement these kinds of attention mechanisms where you're looking at the last thing
Yeah.
matched. And the way you do that is using position encoding.
Yes. Their proof for showing this f of I thing is 3 pages long, and so it's something we started to glance over for this presentation.
Where is the log and precision used?
Where is the log and position used?
It's used when you want to get the current head position.
Yeah.
You take the average of all of the head movements in the past,
Yeah.
but there are potentially n of them.
Yeah. It's in these denominators I,
Yeah.
So you get a very, very small number, and then you hope the layer norm will sort of undo the scaling on that number, but that can only work if the scaling is not so small that the number becomes zero.
Mhm.
Yeah.
Mhm.
And then basically you're also able to, with the same query key mechanisms, output this to another output tape. But that's the gist of how they get their lower bound proof for the transformer. And that basically concludes it for our presentation. So sorry for keeping you here 20 more minutes.
Yeah. Oh, it was interesting.
Is there?
So what's the conclusion about this precision? If you only have fixed precision, then
Yeah.
it seems to me that we will run into problem with using the attention for
So,
very long.
so Shaba, I think that this is not such a big problem because the precision is effectively happening because we have to be able to store all possible head positions, right? Like if you're, and so like even in the normal Turing machine, right? Like if you have a tape of a certain length and you want to be able to store head positions, then you need like log of as many bits, like or like whatever the number of head positions is, which is the length of the tape, you need log of that many bits, right? Like it's not clear how you would implement a Turing machine, like even a random access machine, without being able to store numbers which represent all of the memory
Right.
tape vectors.
Right. Yeah. But except here, you do have sort of something like a tape, but right? Like if you screen really hard, then you see the transformer as the controller, except that the problem is that you're only writing in one direction in a way, and if you limit the precision, then you are, because of the operations it has, you're effectively limited of what you can access from the history that you have written. So you will not be able to build up a lot of memory.
I guess in their theorem for this, they also say that they're assuming that the transformer runs for TFN steps, where TFN is polynomial. So if we have polynomial decoding steps, it's assumed that we can represent the log n bits. I'm not sure. Will the number of decoding steps also, like, if we're constraining that, does it sort of make this realizable with the log n bits?
It just scales with the number of decoding. If it's polynomial, then
Yeah.
it's okay.
Also, it seems like this whole proof should work just as well for random access machines. Like you're kind of simulating a random access machine anyway.
Yeah.
So it seems like it might almost be easier to do
Yeah.
with the random access machine.
Right. Okay. Well, thank you.
Thank you guys.
See you. Good night.
Bye.